AI systems continue to proliferate and become an integral part of various intellectual and industrial domains, including healthcare, finance, and transportation. However, it is well known that these deep learning neural network-based models almost invariably function as black boxes, with limited transparency and interpretability of their decision-making processes. The main advantage of using generative models over current state-of-the-art black box approaches would be interpretability and audibility. Active inference offers a comprehensive framework for naturalizing, explaining, simulating, and understanding the mechanisms that underwrite decision-making, perception, and action. Active inference denotes a family of models premised on the free energy principle, or FEP, which are used to understand and predict the behavior of self-organizing systems. In particular, active inference models the way that latent states or factors in the world cause sensory inputs and how those factors cause each other, thereby capturing the essential causal structure of the measured or sensed world. Active inference modeling has been deployed in the context of introspection, self-modeling, and self-access, which has led to the development of several leading theories of consciousness. Introspection, which is defined as the ability to access and evaluate one's mental states, thoughts, and experiences, plays a pivotal role in self-awareness, learning, and decision-making, and it's a pillar of human consciousness. Self-modeling and self-access can be defined as interconnected processes that contribute to the development of self-awareness and to the capacity for introspection. In the context of self-access, the transparency and opacity of introspection processes have been modeled using a 3-level generative model. The model depicted in Figure 3 provides a framework for understanding how we access and interpret our internal states and experiences. The blue level, which implements the selection of overt actions, can be seen as a transparent process. The orange, hierarchy superordinate level, which implements action and covert action, represents more opaque processes, which make processes in the first layer accessible to the system. This layer models mental actions and shifts in attention that we may not be consciously aware of or able to report. The second level takes as its input the inferences or posterior state estimations ongoing at the first level, as data for further inference about the system inferences. Attentional processes are of this sort. They are about cognitive processes and action, and they modulate the activity of the first level. The green, the final level, implements the awareness of where one's attention is deployed. In other words, it both recognizes and instantiates a particular attentional set via bottom-up and top-down messages between levels, respectively. On the whole, this 3-level architecture models our self-access and introspective abilities in terms of the processes regulating transparency and opacity at the phenomenal level of description, or attentional selection at the psychological level.
If you're familiar with any Markovian process, the present is the Markov blanket that insulates the past from the future. So it's a permeable, because it's based upon conditional independencies, it's a permeable boundary or barrier or blanket, allowing, in the case of just a simple time process, information, as we saw in Milo's talk, to go in one direction, but more generally in this instance, it can be permeated, it is open in both directions, but provides a separation in the sense that if I wanted to predict the internal states from the rest of the universe, it is sufficient to know the blanket states, because there's a conditional independence between the internal states and the external states. So everything I need to know about the internal states in terms of being able to predict it probabilistically is contained within the Markov blanket.
In conclusion, the integration of introspective processes in AI systems may represent a significant step towards achieving more explainable AI, By leveraging explicit generative models, as well as attention and introspection mechanisms, we can design AI systems that are not only more efficient and robust, but also more understandable and trustworthy. This approach allows us to bridge the gap between the complex eternal computations of AI systems and the human users who interact with them. The basic idea is that for a system to report or evaluate its own inferences, it must be able to enact some form of self-awareness, where some parts of the system can take the output of other parts as their own input for further processing. This has been discussed in computational neuroscience under the rubric of opacity and transparency. The idea is that some cognitive processes are transparent, like a clean, transparent window. They enable us to access some other things, say a tree outside, while not themselves being perceivable. Other cognitive processes are opaque. They can be assessed per se, as in introspective self-awareness, i.e. aware that you are looking at a tree as opposed to seeing a tree. The idea is that introspective processes make other cognitive processes accessible to the system as such, rendering them opaque. Another paper by Karl Friston et al. It's called Designing Ecosystems of Intelligence from First Principles. So this white paper presents active inference as an approach to research and development in the field of artificial intelligence, otherwise known as AI, with the aim of developing ecosystems of natural and artificial intelligences. The path forward in AI is often presented as progressing from systems that are able to solve problems within one narrow domain to so-called artificial narrow intelligence, or ANI, to systems that are able to solve problems in a domain in a general manner at or beyond human levels, what are known as artificial general intelligence, or AGI, and artificial superintelligence, otherwise known as ASI. They present this thing called active inference. It's a very general formative intelligence, understood as self-organizing process of inference. Yet the generality of the formulation is integrative, rather than adversarial or exclusive.
Things do exist: grains of sand, rocks on the moon, trees, so all of these things can be separated from the environment in which they are immersed, and therefore they must at some level be optimizing their free energy, taking this sort of model evidence interpretation of this quantity. That basically means they're self-evidencing. Another nice little twist of phrase here is that you are your own existence proof, statistically speaking, which I don't think I said that, somebody did, but I love that phrase. The step through to answer your question about what's it good for, we go along the following lines. First of all, you have to define what it means to exist, which now, as you've rightly pointed out, you have to define what probabilistic properties must the states of something possess so that it knows where it finishes. And then you write that down in terms of statistical independences. Again, sparsity. Again, it's not what's connected or what's correlated or what depends upon what it's what's not correlated and what doesn't depend upon something. Again, it comes down to the deep structures, not in this instance hierarchical, but certainly the structures that emerge from removing connectivity and dependency.
Active inference, it combines the virtues of a first principles physics-based approach to AI with Bayesian formulations, thus reframing and extending the methods found in Bayesian approaches to machine learning, which provide the foundations of state-of-the-art AI systems. It entails an explicit mechanics of the beliefs of agents and groups of agents, known as Bayesian mechanics, which is uniquely suited to the engineering of ecosystems of intelligence, as it allows us to write down the dynamics of sparsely coupled systems that self-organize over several scales or levels. So you can sort of imagine it it's like a hierarchy, and between the hierarchy we have different levels of sparsity. So The sparsity is distributed into various layers or scales of the hierarchy. And this is the coupling, the boundary between each layers of the hierarchy is the coupling of the system. And now the question is, how does this hierarchy self-organize? How does it emerge? And this is sort of active inference is proposing. Observations of nature suggest that simpler and more complex forms of intelligence are almost always related to compositionality. So appreciably intelligent things tend to be composed of systems that are also intelligent to some degree. This communal or collective aspect of intelligence is also reflected in the epistemology of intelligence from the definitions. So they do pull out the definitions of intelligence. So intelligence has inter, right? So which means in between, and then it has ligare, which means to choose or to read. So literally interlegibility, or the ability to understand one another. So they say, but how do we engineer systems like these? Okay, so the authors, they argue that it can be achieved by moving away from asking, how does intelligence present to us as researchers? So, which focuses on empirical descriptive adequacy and reasoning by analogy, for example, the Turing test or the imitation game. Instead, one must ask the more fundamental question, what is it that intelligence must be? So given that intelligent systems exist in nature, such as an approach aims to deduce fundamental properties of intelligence from fundamental considerations about the nature of persisting physical systems. So for example, from first principles, to exist as an individuated thing is to gather observational evidence for such a model. So now they are introducing self-evidencing. So this model evidence can be scored by a scalar value that conveys the degree to which some of these observations conform to the predictable form of the model. So basically it's the emergent properties from the observations that form. You can imagine like a predictive model that forms from the observations. And then to account for perception, one can update variables in order to maximize modern evidence or model evidence and update beliefs to match the data. To account for learning, one can update parameters in order to maximize model evidence and update models to match the data. To account for action, one can select actions in order to maximize or expected model evidence, assuming that the model encodes preferences in terms of prior beliefs. From this perspective, model evidence is the only thing that needs to be optimized. Importantly, model evidence can be approximated in a form that has interesting decompositions into quantities that map onto distinct facets of intelligence. Probabilistic approaches to AI provide a normative theory for learning, starting from the first principles of how AI should deal with data and uncertainty. The main compositional task in probabilistic inference is marginalization, whereas in traditional AI it is the optimization of parameters. As such, a focus on optimization per se in contemporary AI research and development may be misplaced to some extent. Current state-of-the-art AI systems are essentially general-purpose optimization machines. So this is the current state of the art. But now, built to handle a specific task domain, but optimization in or itself is not the same as intelligence. So Friston and company here are saying that this sort of organization, this sort of general model is not the same as intelligence. Rather, in an intelligent artifact, optimization should be a method in the service of optimizing our beliefs about what is causing our data. Well, they argue in this sort of in this paper that such a updating system of updating beliefs would also be needed, rather than what we have with GPT-4, Claude 2, or Llama 2. These models, all of them are static. It's static. After you train it, it's done. You know, it's It doesn't consistently do this updating of its beliefs. If anything transpires between its training completion and future, it wouldn't know all these events, so it's sort of a snapshot in time, rather than a continuous inferring belief updating machine.
What about turtles all the way down and turtles all the way up? Okay, what's the next level? Well, the next level is now the structure. So now for any given graph, for example, that is equipped with edges, and those edges will have to have some slowly varying parameters that describe the nature of the message passing on those edges. There will be you are conditioning upon a particular structure, and is there a connection there? Is it hierarchical? Is it heterarchical? Is it a U-net? Is it a transformer? Is it a convolutional neural network? You've seen this wonderful evolution of structures in machine learning over the past few decades as people try out different structures, and some work for one kind of application, others work for others. But from the point of view of your question, what we are seeing is a kind of structure learning that's playing out over years. Yes. But it's exactly the same principle. It's this free energy minimization, but just in this instance, the free energy now is a pathological. It's just the average over a long period of time, which is exactly the quantity that people doing structure learning or Bayesian model selection use when adjudicating between different graphs, usually of complex system models, for example. And you could argue that now, over several tens of years or hundreds of years, that exactly the same maths could be leveraged to provide a formal description of natural selection as Bayesian model selection. Exactly the same thing as you're doing now when you're selecting whether to speak or whether not to speak, or trying to infer, selecting the right hypotheses about the narrative that you have in your head that makes sense of what I'm saying. Exactly the same maths and mechanics is unfolding over the millennia, in terms of evolution.
Okay, so they go on to say state-of-the-art AI designed for action selection typically implements reinforcement learning, a set of methods for maximizing the expected sum of rewards under a sequence of actions. From a Bayesian perspective, however, curiosity and exploration are as fundamental to intelligence as maximizing reward. Specifically, the epistemistic, exploratory, curiosity-driven aspect of intelligence motivates actions expected to reduce uncertainty in the variables and parameters that define your model, which in the active inference formulation corresponds to inference and learning. In line with the above discussion of self-evidency, rather than select actions that maximize some arbitrary state-dependent reward or equivalently minimize an arbitrary cost function, an intelligent system ought to generate observations or sensory data consistent with its characteristic. Otherwise, they say, i.e. preferred exchanges with the sense world, and thus with its own continued existence. That is, an intelligent agent ought to maximize the evidence for its generative model. Active inference thereby generalizes the notion of reward and labels every encountered outcome and explicitly every latent state in terms of how likely it is that this would happen to me. Next up, they're saying here they have noted that intelligence as self-evidencing is inherently perspectival. This brings us back to the insight that intelligence must, at some level, be distributed over every agent and over every scale at which agents exist. Active inference is naturally a theory of collective intelligence. Yeah, you see, so the contrast between reinforcement learning, right, is that, again, it models some very, very specific goal, whereas active inference it's more like reverse. It's an inverse reinforcement learning, where you see these actions, right, and then you sort of then derive the goal. When AI takes the initiative to ask us questions, we will have moved closer to genuine intelligence, as seen through the lens of self-evidencing. Now, the authors argue that the future of AI would benefit greatly from a focus on optimization for shareability, or gathering evidence for a model of integrally social creature. This might take the form of a shared external store of knowledge about how to communicate with relevant others, or a stored structured communication protocol that can act as the lingua franca of AI. A general framework that ties together different embedding spaces and inter-AI messaging over a shared network architecture would, among other things, enable AI agents to learn to offload certain tasks or predictions to other, more specialized AI agents. What results is a shared intelligence, a kind of collective superintelligence that emerges from an ensemble of agents. Operationally, ecosystems of shared intelligence can be described in terms of message passing on a factor graph, a special kind of graph or network in which nodes correspond to the factors of a Bayesian belief or probability distribution. Factors are just probabilistic beliefs that one multiplies together to get a joint distribution or a generative model. Keep in mind, when they say generative model here, they actually mean active inference. They don't actually mean LLM. For example, one could factorize beliefs about the latent states of an object into what and where. The Bayesian mechanics of intelligent systems that follows from active inference led us to define intelligence operationally as the accumulation of evidence for an agent's generative model of their sensed world, also known as self-evidencing. This self-evidencing can be implemented using message passing or belief propagation on a factor graph of networks. So active inference is uniquely suited to this task because it leads to a formal account of collective intelligence. So yeah, these are my notes from this. So one of the notes would be like, they were saying, for instance, an upper bound on the model evidence called variational free energy can always be written as an accuracy minus complexity. You see, so when a system minimizes this bound, in so doing it automatically maximizes the predictive accuracy of its model while minimizing its complexity. So as noted, this sounds very familiar, of course, because it's Occam's razor. Occam's razor. It's quite famous in statistics. Basically, it's this idea that out of a selection of a few items or possible solutions, the one that looks the simplest or most simplistic is typically the correct one. So that's Occam's razor. So this means that self-evidencing mandates an accurate account for sensory exchanges with the world that is minimally complex, which serves to limit overfitting and poor generalization. Another note I had was it mandates information and preference-seeking behavior where one contextualizes the other. The ensuing curiosity or novelty-seeking thus emerges as an existential imperative to the extent that one could say that to be intelligent is in part to be curious and to balance curiosity against preferences or reward in an optimal fashion. But yeah, it's a great idea. I mean, this paper is very good. And keep in mind, this one does not contain any mathematics, but there's other ones which do contain more math. This one is more so just a white paper of a potential direction where AI could go. But yeah, I think that's it.
This notion of epistemic affordance that you get from these simulations, where this is just about lever pulling. This is basically what would happen if I did that. This, I think, is one of the most beautiful expressions of this imperative to reduce uncertainty. So remember, mathematically, free energy upper bounds surprise, and expected surprise is uncertainty, it's entropy. So all that we are saying here is that we are things that act to minimize uncertainty. Now, one of the best ways to act to minimize uncertainty is to see what happened if I did that. So when you look at the posterior beliefs over the consequences of action, what would happen if I pull that lever? That becomes incredibly attractive from the point, in the jargon of Gibsonian people and the inactivist movement. It has epistemic affordance. So this Bayesian surprise, or this mutual information, if you're Horace Barlow, I think it's probably more easily understood as this intense epistemic affordance or attractiveness. So the yellow lever, the lever in the yellow submarine, if it has not been pulled before, all other things being equal, has the greatest affordance because it's novel. So when you rewrite this Bayesian surprise, not in terms of posterior beliefs about states of the world, but posterior beliefs about contingencies, the parameters that generate states of the world, the consequences of action, that looks exactly like novelty.